back. Today we're going to go through another application of differentiation. It's called optimization. It's essentially referred to applied maximum or minimum problems in the literature. In particular, today we're going to try to maximize the area, which is for a Norman window. So let's just try to read the statement of the problem. We have a Norman window constructed by adjoining a semicircle to the top of an ordinary rectangular window. So you have two pieces. The question is asking us to find the dimensions of a Norman window of maximum area if the total perimeter is 18 feet. And here is a good outlook of the Norman window. As you see that you have a rectangular bottom, and then on top of that you have a semicircle. But before we step forward, why don't we remember the guidelines to solve applied maximum or minimum problems? So first of all, we're going to identify all given quantities and all quantities to be determined to start with. And as you see that we already made a sketch to help us to figure out the area or the perimeter. And we're going to write a primary equation for the quantity that is to be maximized or minimized. For our problem, it's going to be the area, total area for the Norman window to be maximized. And next, we're going to reduce the primary equation to an equation having only one independent variable. And then we're going to determine the feasible domain of the primary equation. And finally, we're going to try to find the maximum value of the one single independent variable function. And here's a sketch of the problem. So essentially, when you have a rectangle, you have two sides. One is the bottom one, the other one is the side one. So width or height, you can call it that way. So I call the width to be 2x and the height to be y. The reason why I chose this to be 2x is because we have a semicircle right at the top of the rectangular piece, and that comes with radius. In fact, the radius is the half of this length, as you see, so x and x. So x is in fact the radius of the semicircle. This way, we know the radius of the semicircle together with the two sides of the rectangle. We can talk about the area, some of the areas and perimeter of the Norman window. Well, to start with, let's write down the primary equation. Okay, primary equation is the one that we're trying to maximize. So we're trying to maximize the area of the Norman window, but the area consists of two pieces. One is the area of the rectangle, the other one is the area of the circle. Well, the area of the rectangle is 2xy. And the area of the full circle is pi times radius squared, but radius is x. So pi times x squared is the area of the full circle. We have the half of that, so this should be pi x squared over 2. All right, what is the secondary equation? Well, secondary equation is the constraint that's given to us. The perimeter is going to be 18. You have the top piece here and the bottom piece here. So for the bottom piece, you have three sides only. So one lateral side, another lateral side, and the bottom. So 2x plus 2y plus the perimeter of the half circle. So, well, for the full circle, the perimeter is 2 pi times the radius. And for that reason, it's 2 pi x. But we have the semicircle, so it's going to be the half of that. So pi times x is the perimeter of the top circle. And what we're going to do here is that we're going to set this to 18 because that's what the question statement says. Okay, this is our constraint for x and y. And now we're going to solve the secondary equation for y. If you want to do it for x, go for it, no problem. We're going to do the same type of calculation. But let's try to solve this equation for y. So y equals, in fact, 2y equals 18 minus 2x minus pi x, and divide everything by 2. So it's 9 minus x minus pi over 2x. All right, so once we have y, why don't we plug that back into the primary equation? And I'm going to call that equation to be f of x. All right, f of x is equal to 2 times xy. Well, in other words, 2y times x. So let me just write 2y from here. Okay, 2y times x. Here we go. plus pi times x squared over 2. Let's see if we can simplify this. So 18x minus 2x squared minus pi x squared plus pi x squared over 2. All right, so these are like terms. So 18x minus 2x squared minus pi x squared over 2 is the simplified version of the function of one independent variable x. In the next step, we're going to find the domain, feasible domain of this function. And once we have it on that domain, we're going to try to find the maximum value of f. Well, the feasible domain is determined by the physics of the problem, obviously. So, well, since we have the radius x and the height y, obviously we want x and y to be positive to start with. And as you see from the constraint equation, we have y determined to be 9 minus x minus pi over 2x, and we want this to be positive. What that means is x plus pi over 2x should be less than 9. And if you pull out x should be smaller than 9 over 1 plus pi over 2. All right? So x is going to be smaller than this number. But in the meantime, x is going to be greater than 0. And this is our feasible domain. This comes out of the fact that y coming out of the constraint or secondary equation has to be 0 because y is the height of the rectangle. It can't be 0. Okay? All right, so on this domain, we're going to try to maximize this function. In other words, we're going to apply the first and the second derivative tests to find the critical points and check for which one provides us the maximum value. All right, let's look at the first and the second derivatives. So f prime of x is equal to 18 minus 4x minus pi x, and f double prime is going to be minus 4. This is a good news because f double prime is negative, so the critical points, in fact, are going to generate maximum values. So we have two types of critical points. One is the one making this f prime undefined, which is not the case here because this is a nice linear function and it's defined for all x. But the second critical point comes out of setting this equation to 0. In other words, we're trying to find the x's that make f prime 0. And let's just solve this. So 4x plus pi x is equal to 18. And x factored out, 4 plus pi equals 18. And then x is 18 over 4 plus pi, which is equal to 2.52. Okay, that's good news. So I can go ahead and find the corresponding y value out of this constraint, which was this. Okay, you can go ahead and find the corresponding y value for it. And this critical point is in this interval because this number here is approximately equal to 504. Okay. So, well, definitely 252 is way less than 504, and it's a positive number. You can go ahead and find a y value accordingly. All right, here is the graphical outlook of the function that we were trying to maximize here. And as you see that 252 is the point where the maximum value is achieved. And as you see that the function has a local maximum here, in other words, flat tangent line here, and the corresponding maximum area is 22.684. Let's also try to find the y value here. Since x is found to be 2.5, the perimeter is fixed, which is pi x plus 2x plus y. and that should be equal to 18. So we plugged the x value back into the y equation, and we got y, in fact, equal to x. That is also 2.52, and the corresponding area, as I showed in the previous graph, is 22.684. So this is a good rectangle. In fact, you have like two squares in this rectangle because if you divide this by half, this is a square and this is a square, and you have like quarter circles on top of the squares here. So what is the benefit of getting the maximum area? It could be something like you may want to get the most sunlight in the room. So if you design your normal window that way, you will get the most sunlight in. All right, this ends the video. Thanks for watching. I'll see you in another video. Bye.